Welcome to the shop. This is the first video in a series of videos where I make a run of 10 sets of parts for the NQALHA project. I'm going to be showing every step I can, but you know, sometimes cameras run out of batteries, things go wrong, and so I probably won't get absolutely everything, but I plan to do as much as I can. So for the first step, I'm going to do a little setup and a little preparation. I'm going to go over here and get a fresh new bunch of end mills here. This little guy is called the aluminum shredder from Lakeshore Carbide, and it's an excellent roughing cutter. And this guy is a 3-flute zirconium nitride coated end mill specifically for aluminum. And let me go ahead and turn it on here. When it's first turned on, it needs to be referenced. The Tormach mill is a stepper motor machine. It doesn't have encoders on the axes. It only has stepper motors, open loop stepper motors, and it has mechanical limit switches. So when the machine starts up, it runs the axes slowly toward the mechanical limit switches, and then when it hits the limit switch, it defines that as the end of travel. This is surprisingly good. It actually can reference the axes within a few thousandths. I've sometimes thought about that it might be a kind of a cool thing to replace the mechanical switches with more precise switches so that the machine would reference itself within tenths, but at the moment it references itself within a few thousandths, and I always use the Hymer Indicator to get it more precise, to increase the precision of the location. In addition to that, I use a variety of different work offsets. I've got the left and right vise. Let me go over here and run I'm running a G-code here that I call the setup G-code, and it basically just sets all the parameters that I commonly use for most operations. I've got a left and a right vise. I'm using soft jaws, and the soft jaws are milled on the Tormach out of aluminum, so the ledge here is accurate relative to the machine. I like soft jaws for a couple of reasons. First of all, as you can see by all of the little dings and divots here from drill bits extending through the material and touching, if I use a hardened parallel, I have to be really, really careful when drilling holes close to the edge. With the aluminum soft jaws, the ledge is still a perfectly valid reference surface. The little divots don't affect its utility as a reference, but I don't have to be as concerned. Obviously, I need to be concerned about the socket screw, but it hasn't been a problem. The other thing is just kind of practical, that unless you have like parallel holders, the parallels tend to fall over when I blow the chips out. So I'm gonna, talking about work offsets, don't want to get out of sequence here. Work offset 1, G54, is located at this point, at the left and rear of the right vise. Work offset 3 is located over here, left and rear of the left vise. Those are the ones I use most often. Work offset 2, 4, and 5 are specials that are used for special cases. And today I'm actually going to be using one of the specials. I'm going to be using work offset 5, which is located at the right side of the right vise at the rear. And I'll be showing why that's used as the project proceeds. The surfaces here, the clamping surfaces of the two vices, were aligned with the indicator when the vices were installed, so they're in line. So when I'm milling a larger part, which is what I'm going to be making today, I can put the part in both vices and have the back end aligned to the rear reference plane. So what I'm going to do now, I'm going to go over to the automatic tool changer here. The tool changer is going through its startup procedure now, and it's going to grab tool number 3, which is my older cutter. And really there's nothing wrong with this one, but just, I mean, I will keep it. I'm not going to trash it, but just to start this process off in the best possible condition, I'm going to put fresh new cutters. Now, obviously, since I put the cutter in by hand, who knows where the tip is? Might be anywhere. So I'm going to take the Z-axis measurement device here, called the electronic tool setter probe, and wipe off the surface of the vise, wipe off the surface of the spindle. This is the reference surface on this part of the spindle. This part is where 0 is referenced from, and the tool length is referenced from the mating surface of the tool holder and the tip of the tool. So first step is to tell the machine where this reference surface is. And let me go over here to manually jogging using the Tormach little USB controller. It's not a very good jogging controller. I've been thinking, hey, maybe sometime if I get a whole bunch of spare time, maybe I'll invent a better jog control for the Tormach, but too many ideas, not enough time. Oh, here goes. So I have now referenced the bottom of the spindle to the surface of the vise because the routine knows the height of the measurement unit. And now I'm going to insert the tool. It's going through the automatic tool height setting routine. And I'm going to store that tool in the automatic tool changer. I've got some other tools in the tool changer left over from yesterday's work, and I think I'll remove those because I really only need the tools that I'm using today. Every tool goes into its hole on the rack, with tool number 1 being at the upper left. Every tool is numbered and every hole in the rack is numbered, so I can keep track of my tools. I also put, let me see if you can see it here, I also put the tool number on the tool holder to make it even easier to avoid making mistakes. There are so many mistakes that can be made in CNC machining, so many things to remember. People who haven't done CNC machining believe that, oh, it's just automatic. The machine does all the work. Well, after it's set up, after it's calibrated, after the tool path is tested and proven, after everything is lined up and adjusted, yeah, pretty easy. You can have an untrained operator, commonly called a button pusher in the business, just put in a part, push the go button. But there's a whole lot more to it than that. You still need to be a machinist. You still need to know feeds and speeds. Still need to know the tricks of creating tool path. Set the tool height or the tool length of the roughing cutter. And now put away this guy for a moment and grab the Hymer Indicator. The Hymer Indicator is really an excellent tool. It's a three-dimensional indicator, so it measures up and down, side, left and right, forward and backward on the same dial, and can be used for setting X, Y, and Z. It internally is calibrated with the diameter of the ball on the end, so when you move, and let me get this done here while I'm talking. So now I'm jogging around very slowly with the Tormach jog wheel and getting the 0 on the indicator. What that means, the indicator knows the diameter of its sensing ball, so when the indicator reads 0, it means that the center line of the spindle is aligned with the edge of the workpiece. So going over here to set the 0 on the machine, and got to be very careful. The machine is really powerful. It can break the tip of that indicator before you even know it, so it's always important to really pay attention when using the indicator. So now I have zeroed my test block, and I probably should talk a little bit about why I'm doing this. This is the test block of scrap aluminum. I'm going to put the 3/8 finish mill into the spindle and cut a pattern, which I'm then going to measure with a micrometer and see, is the pattern the dimension that I expect it to be? Because even though the nominal size of the 3/8 end mill is 375, well, you know, it is a ground tool. It might not be 375. It might be a half a thou off. So the part that I'm going to be making, I actually care about dimension. Some of the other parts that I'm making, plus and minus 5 is okay. The part that I'm going to be making, I actually want to get it a little bit closer. I want to get it within a few thou. And so I'm going to be verifying the diameter of the cutter and the cutter compensation in the G-code, and if necessary, adjust the cutter compensation in G-code. So it's not super important in this to perfectly accurately set the height. I could probably just get by with setting it by eye for this test piece, but hey, it's so fast with the electronic tool setter. So now I've defined Z0 as the top of this part. And I'm gonna load up the test pattern, which isn't currently on the machine, so I gotta go over in the office. My office is right next door to the machine shop, and all of the machines, the CAD machine and all of the CNC machines, are on the network, so I don't have to carry around floppy disks or USB sticks or anything. So this is a new program, never been tried before, and I'm going to go through my new program setup, make sure the part is clamped in nicely. When I start a new program, and okay, so that's wrong. My CAM program, my toolpath program, has an annoying characteristic of selecting automatic tool numbering and ignoring my defined tool numbers by default. So once again, so many things to remember. So loading the tool, gonna set the okay, well that's wrong. So this is a really annoying characteristic of the Tormach controller. And remember what I said, there are so many things to remember about this thing. And of course, it doesn't make it easier when I'm trying to narrate, improvise narration on a video at the same time. But here's what happened. I set the tool length of tool 48, the roughing cutter, and then manually removed the roughing cutter from the spindle to set the 0 height of the top of the part. Well, it turns out that the Tormach controller still thought the tool number 48 was in, and instead of setting the 0 height to the spindle, set the 0 height to the tool end, resulting in the 0 height being set incorrectly. So let's see if I can get it right this time. Like I said, there are so many things to get right, and when I'm doing a new program for the first time, I've got my finger on the e-stop button constantly. So now, and of course, if I was going to send a message to the Tormach programmers, I would say either warn that there's a tool in the spindle, or it thinks there's a tool in the spindle, either give a warning or an error message, or simply ignore the tool and reference to the spindle, but silently referencing to a non-existent tool? Wow. Okay, substantially better. And of course, because I was aware of what's going on, had my finger on the E-stop button, saw that it was going wrong before it had a chance to go wrong, didn't break the cutter, didn't ruin the part. It annoyed me a little bit, but oh well. So here we go. Let's try it again. Going into single step mode after the tool is loaded. And okay, the toolpath software puts in a rapid motion to an inch above the surface as the first step in the operation. And I verify by eye in single step mode that yes, in fact, looks like I'm about a half inch, I'm about an inch above the surface. That looks reasonable. It's a nice little sanity check. And the other one, as I saw the tool continuing beyond the inch, hit the E-stop and avoided damage. So here we go. Making a test cut, both a rough cut and a finish cut, and I'm using a similar size of finish cut, which is 15 thousandths. This is similar to the finish cut that I use when I'm actually making my part. So it should be representative of tool deflection, and should give me a very accurate measurement of what the actual cutter diameter is. So there we have the test part, and I'm now going to go get the micrometer. Well, that is showing 4 10,000ths over the programmed size. I'm going to call that good enough. But it's always nice to do this check, because in the past I've had problems where either because of tool wear or just because of manufacturing tolerance, the cutter isn't exactly the nominal size. So let's go over, store that tool. The Tormach tooling system, get a clean paper towel. The Tormach tooling system it works, but it's a bit, I don't know, I wish it worked better. It's got a collet in here that grips a smooth surface on the tool holder. And it's important that these surfaces be really clean, because especially when taking a heavy roughing cut, any oil or coolant or any contaminant in the mating surfaces can cause insufficient clamping force and end up with tool pullout. This is more than the rigidity of the machine and more than the horsepower of the motor. This is the limiting factor in the Tormach, in the Tormach PCNC 1100 Series 3. The limitation of taking heavy cuts is mostly the pullout of the TTS tool holder. The new generation machines, the MX machines, have a industry standard. I think it's like a BTS 30 tool holder with a better retention. I think Tormach realized that the TTS tooling system was inadequate, and so they fixed it. But unfortunately, I'm stuck with the old one. So the part that I'm going to be making here is a long part. I'm going to be making the top vertical arm, part number 400, for the NQALHA, and it's a long part. It's 12 or 13 inches long, and so I need to use both vices. So I'll be using work offset 3, which is G56. I had to think for a minute. And let me go over here to what it thinks is 0. And of course, if I was doing less precise work that I didn't care about as much, then, yeah, there we go. If I was doing work I didn't care about as much, the system remembered the last time I set 0 for this work offset, and it probably would be close enough. But today I'm going to go through the whole cycle, partly because I do care about accuracy, and also just because I'm making a video and it might be informative to show the entire process. So okay. Whenever I'm jogging the machine with the Hymer in place, I always go slow, really slow, painfully slow. I don't like breaking off Hymer tips. So now 0 has been defined, so I've got a stop here that is threaded into the end of the vise, and of course the edge here was precisely milled to be perpendicular and flat and nice, and then I've got a stop that I screw in, but for using the 2 vices, I'm going to take the little stop off, put it over here, and I am now ready to start making a part. So, back from the CAD system in the office, this is a known part that I've made before, and my previous toolpath was pretty close, but in the previous versions of the part, I used the material I had in stock, which was a tiny bit wasteful, and since I just got some new material, I redid the toolpath, tuned it up a little bit, changed a couple of feeds and speeds, and rearranged it to make better use of the more correctly sized material. I have here, you can see it on my little clipboard, I have my setup sheet, and that tells me a lot of things about what I need to prepare for, how big the how big the blank is, and what tools to use. I also, let me go over here to the user interface on the network. The system also tells me what tools I need to load. So I'm going to go ahead and load up a carousel, being careful to clean the shaft, clean the surface. So number 23. Number 24, the Tormach doesn't support real rigid tapping. It does support power tapping using this special tapping head called a compression, I think it's a CR, compression release or something like that. It's spring-loaded, and so the head is doing its best. It doesn't have an encoder in the spindle to measure spindle RPM. It's kind of roughly calibrated when I set up the machine with a tachometer, so it kind of sort of knows how fast the spindle is rotating, but it's nowhere near precise enough to do real rigid tapping. It gets as close as it can, and then the various different the slop in this tapping head takes up whatever inaccuracy remains. So, and yes, it does work. I wish I had real rigid tapping, but so far I've tapped hundreds of holes and haven't broken a tap yet. Well, except when I make a mistake. So, most of the drills that I use are the stubby drills. I like the stubby drills because they don't require a pilot hole or a spotting hole or a center hole or whatever. They just drill straight. This one is still a full-size jobber length, and you know, it's heavy enough that it'll drill an accurate hole. Of course, this drill is not the final size. This drill is the rough size for a reamed hole. So I kind of get a second chance with the reamer to get it a little better. And yeah, I know all the purists out there are probably going to be saying, no, a reamer won't fix a misaligned hole, but in the, I don't know, 100 parts that I've made with this technique, they all work well enough. So sometimes close enough is good enough. And number 41. Number 43. Very few parts of the NQALHA require high precision. A few parts, very few, require the part to be made within a tolerance of 1,000th or so. For most of the parts, plus and minus 5 is okay, and actually for many of the parts, since that Close enough is good enough. Really, surface finish matters more for the aesthetics, like on the outside profile of most of the parts. The surface finish matters more to the way it looks, and the actual dimension, well, it could be anything, as long as it looks about right. But still, I try to make everything as precise as I can, just because I like precision, I like practicing precision, and I'm not going to go crazy and try to get every single dimension within a tenth, but I like to be kind of close most of the time. So now I'm going to go get my stick of material. I'm using aluminum extrusion, extruded flat bar, for pretty much all the parts on the NQALHA. My end supported here. So refer to the setup sheet. The blank is 12.4 inches. And I usually make it just a little bit longer. The saw that I'm using here is a cold cutting metal saw with a carbide blade. Yep. And I'm using a blade specifically ground for aluminum cutting. Also got a little stop that I improvised over here so that I can make repeated cuts. I use a little WD-40 as a cutting lubricant, and the cut is really, really nice. It's smooth, it's nice, almost no burr. I still go over to the Scotch-Brite and just give it a little hit. Now, one thing that is strange about this setup that I kind of didn't do right away, probably ought to do it now before I forget. This one uses work offset 5, which is one of the special work offsets, and that's going to be G58. And that puts the 0 at the right side. And I haven't used this one for a long time. Let's see how the machine remembered it. And the machine didn't remember it at all. It must have been set up differently. I almost never rely on the machine remembering anything. Only for extremely non-critical parts where I'm being lazy, but most of the time I do it right. So let's go ahead here and sure everything is nice. And now, program that I'm using here is a program that I made. It's a combo program that's composed of two programs that were made on the toolpath. So the CAM system made two programs, and then I kind of manually edited them together, editing the G-code. So this is, even though it's based on a known trusted program, this is still the first time through, and so I treat it as if it was the first time through and do everything according to plan. So I'm going to run it in single step mode with my finger on the E-stop button. Single block. Observe that the tool tip starts off at about an inch above the surface. Verify that the flood coolant is correct. RPM looks correct. Everything looks correct. And we're drilling holes. We're going here at, let me read it off my list, 2,500 RPM, 10 inches per minute. And boy, that guy is flinging chips, I tell you. 2,500 RPM, 10 inches per minute, the fast peck cycle, and 150 thousandths for each peck. I'm trying to get the job done quickly because I kind of don't want to stand around all day waiting for the machine, but also I have to be concerned with tool pullout, the limitation of the horsepower of the machine, and I don't want a bunch of chips to build up on the cutter and form a rotating rat's nest. And so it's a kind of a balance between all of these things. So that the cutter is more or less clean, and went kind of quick. So single block, verify correct. This is a 7/8 countersink. The holes, this is a purely decorative feature. I think that the holes in the upper and lower arm on the NQALHA are just there partly to make the part lighter, to make the head lighter, and partly just as a design element. One of my favorite aesthetic elements is holes. Many of my artistic pieces have holes in them, and I like holes. And I think the holes look a little better with a bit of a chamfer. So I'm going to be chamfering the holes at 600 RPM, 4 inches per minute. And getting a little bit of chatter. That I really don't like that. That's too deep, and I'm getting chatter, so this part may end up going in the trash, unfortunately. I'm going to run this part again, and even though I'm not happy with it, the chamfer was too deep. I don't like the way it looks. This part is trash. It's still, why waste the material? I can use it to verify my tool path, and this way, if I have another problem, then I only waste one piece of material. So right now it's just going through re-drilling the holes, just verifying that, yep, the drill operation is still correct. few words about the Tormach mill. It's a reasonable quality mill for the kind of work I do, semi-production, limited production, prototyping. I wish I had a Haas mini mill. I wish I had a more serious production machine, but hey, the Tormach it works well enough for me. It's got some quirks, it's got some behavior that you have to be careful about. Okay, I've changed the machining order here. I think this will be a little bit more advantageous for cycle time. So, verifying in single-step mode that I'm at the appropriate preparatory height, ready for feed. Drilling my 1/4-inch hole, which drilled correctly. This was 3,000 RPM, 10 inches per minute, fast peck at 10 thousandths per peck. So now, going to be moving over to the reamed holes, single block, hand on the E-stop, observing that I'm at the correct preparatory height, observing that I'm at the correct pre-feed height, and drilling with 2,500 RPM, 10 inches per minute, fast peck at 150 thousandths per peck. These holes are reamed holes, and they're the holes that I press the main bronze bushings into. And in the past, I've just drilled them, but sometimes I've had depending on the feed and speed and the condition of the drill bit, I've had inconsistent sizes, and the bronze bushing needs to be a nice press fit. The bronze bushing is 1,000th or 2 over the nominal size, and so I find when I take the extra few seconds to ream the hole, I get a better quality press fit because I don't want that bronze bushing popping out over the years of use. So preparatory position looks okay. Feed position looks okay. I'm reaming at 250 RPM with 5 inches per minute. And going over here to the next hole. It makes the cycle time just a little bit longer, but it makes the result a little bit better. And that's one thing on this project. I love to minimize cycle time and maximize production, but I also want to do a really good job. I want to make these as good as I can make them. So here's a verifying preliminary height. This is going to be an 832 tapped hole. This is full speed, 5140 RPM, 10 inches per minute, with a 60 thousandths peck on the fast peck cycle. I find that sometimes a more aggressive feed rate of 10 inches per minute actually works pretty well to end up controlling the chips. So I'm now going to be doing tapping, and I turned off the flood coolant. When I first started doing tapping on the machine, first started doing machine tapping, I used the flood coolant, and it had some problems. The flood coolant, first of all, this compression tapping head, compression tension tapping head is so long that the coolant just hits the body and doesn't get on the tap. And second of all, this coolant doesn't work that well as a tapping lubricant in aluminum. So I use Tap Magic for aluminum, applied by hand. And yes, it does slow the process down, but it also produces a good result. I'm using a spiral tap, and the spiral tap ejects the chip upward, which is good for blind holes and actually is fine for the through hole I'm tapping now, but many of the holes that I tap in the NQALHA project are blind holes. So now I'm doing the counterbore, not the counterbore, doing the chamfer last, because when I flip the part to chamfer the other side, I don't have to wait for a tool change. So let's watch it go. .500 RPM, 5 inches per minute, trying to avoid chatter. This big countersink does tend to chatter. Okay, and that is exactly the way I want it to look with no chatter. So here comes the part that I put in manually. Let's see if it works. Okay, so it pauses the machine, stops the spindle. And now I'm gonna flip the part over to, let me get rid of some of these. So, yeah, I gotta remember what's what here. Flip the part over, and now 0 reference, because when I started, I had this side as 0 reference. This side is who knows what. It was cut with a Sharpie on a chop saw. Who knows what this is, so I can't really flip the part this way and use that end. I have to keep the reference at this point and flip it over this way and use the right-hand reference to make sure that I end up with my holes where they should be. So, and I also need to make sure that I don't make stupid mistakes. Good thing I remembered that. So for all of you out in YouTube land, if anybody is actually watching this thing, what mistake did I make here? I didn't set 0. Once again, as I said before, and that's why I'm doing the video this way, that in the past I've done my CNC videos where everything is set up, everything is dialed in, and I just show the video of the final operation, simple as can be, as if, boy, this is easy, anybody can do that. But in this case, I am showing everything. I'm showing the setup, I'm showing the mistakes, I'm trying to remember all the steps while improvising a monologue. And let me, okay. So I'm showing all of the steps, because if anybody is actually interested in learning how CNC work is done, it's important to understand the steps and not just see, oh, here it is when everything is set up, everything's adjusted, all the problems are fixed, all the trouble is shot, and here's what it looks like to a button pusher when the setup guy has already finished the setup. So now I'm going to be testing the chamfer. Okay, verifying the preliminary position 1 inch above the surface. Verifying the pre-feed position. So it's back to the CAD system. There's another problem. When I cut the chamfer too far on the first attempt, it was because my zero was off. My tool path was correct. There was nothing wrong with my tool path. And I incorrectly changed my tool path without realizing that I had forgotten to set my part height. I hate making mistakes. But I do make mistakes. And anybody who's trying to learn to do CNC machining, I guarantee you're going to make some too. And the serious ones break a cutter, ruin your part. The really serious ones break your machine. Okay, I'm back under control now. Back to the CAD room. I believe I should be in production, ready to go. So, unfortunately, this part, I'll probably use this part when I'm verifying the outer profile in case anything goes wrong in the outer profile. Okay, something else I do, it's just always nice to remember, and I put a 0 on the part at the reference location, and that way when it comes time to change the fixture, to flip it or do something else that involves changing the fixture, I don't have to remember the geometry of the part. You can just look at that little Sharpie mark and go, yeah, that's where 0 is. So I'm going to run the whole cycle, full speed, finger on the E-stop. I'm very confident this will work correctly, but still, that's a 1/2 inch cobalt high-speed steel stubby drill bit. And once again, I try using stubby drill bits whenever I can. The only time I use a long bit is if it needs to be long in order to reach around a fixture or get into a tight spot, or in some cases I don't have a stubby and I just use a regular and get away with it. So my home-built custom splash guard enclosure here does a pretty good job, and I'm getting a little bit of buildup on the cutter. This splash guard does a pretty good job of containing the coolant and the chips. Those big chips on that half-inch drill bit are coming off at a pretty high speed. And checking, paying attention, everything looks good. Those chips are coming off at a pretty high speed from drilling those half-inch holes as aggressively as I'm drilling them, and it's nice to have this protection. Tormach sells a full enclosure kit for the machine. Let me stop talking and pay attention for a moment here. Yes, Tormach sells a full enclosure kit for the machine, and I really don't like a full enclosure. I like better visibility. I think my homemade, custom-made splash guard provides all the protection I need. I don't require any kind of interlock. I'm smart enough to know not to stick my fingers in the machine when it's running. Okay. This is production run 4 of the NQALHA, and each NQALHA, I'm trying to remember, each NQALHA has about 60 machined parts. So that means I have 600 or so parts to make. And considering that this is the 4th production run, it means that the Tormach has made several thousand parts, successful parts. Okay, I'm paying attention, hand on the e-stop. Yep, all is well. The Tormach has made several thousand successful parts. And like I said, you can always wish for more. A Haas mini mill would have probably cost about twice as much, and it wouldn't fit through the door. This workshop started off as a residential garage, and a Haas mini mill wouldn't fit through the door. This is a kind of a delicate operation here. I'm trying to clear the chip without blowing the chip back into the cutter. In the past, I've kind of been a little ham-handed about it and not really watched what I was doing very well. Oh, out of sequence here. Not really watched what I was doing and got a little too aggressive and ended up blowing the chips back into the hole and breaking my tap. So now my chamfer should come out. Yes. There's my size. So many things to remember. And yeah, at this point, if I had an assistant who could just push buttons, I could just turn it over to the button pusher and go do something else. But hey, one-man shop, I do it all. So, notice that the cutter is pre-positioned, ready to go. Not raising the Z-axis, not doing a tool change. Check to see that my 0 is 0, 0 at the reference. Clear off all the dingleberries. And all is well, I have success. So toolpath is verified, I'm in production. And there we have the first operation. This part requires 3 operations: the drilling operation, the profiling operation, and then there's a perpendicular drilling operation in addition. So there's 3 operations, and the first operation requires a flip. So I'm going to make a very slight modification here to the... Maybe not. Maybe not. So, gonna take the hand deburring tool. Yeah, I probably could have used the countersink to deburr these holes, but hey, I got nothing else to do. Just standing around like a button pusher, watching the machine go. So there we have the first operation completed successfully, the first part of the first operation, and I think I'm going to stop the video right now because the rest of it is just repetition, and I'll restart the video. I'm making 10 sets of parts, and I'll restart the video when I do the outer profile. So, see you later. Okay, I've got the full set of 10 pieces finished. And now it's time to make a new tooling plate. The old tooling plate that I was using previously was for the different size material, and remember I changed the design ever so slightly in order to make better use of the material that I have. And not waste as much. So I'm going to be working on this tooling plate. I just realized that the tool path isn't correct, so back in the office. Okay, So many things to remember, so many things to think about. And let's see if this works. So I'm going to be, since this is a one-off and I'm only going to be drilling and tapping 2 holes, I'm not using the automatic tool changer. I'm just going to manually insert the drill tap, and then I'm going to be drilling and tapping 2 holes. But since this is a new program, have to do the new program drill. So many things to think of, so many things to remember, and of course, trying to make a video makes it even harder. So, single block. Verify the preliminary position looks reasonable. And it does. So, I'm going to do a quick sanity check here. And yes, it looks reasonable. So, I'm going to get my 1/4 tap here. And that is looking reasonable. I think that's not going to be insane. Looks like a happy hole. Happy tappy. So, there's my tooling plate, and it has 2 1/4 tapped holes, and the next thing I'm going to do is just try running the profile without a part in place, just with the tooling plate, and just as a kind of a sanity check for reasonableness. This one I'm going to be starting with the Lakeshore Carbide called the aluminum shredder. It's a roughing tool that does a very nice job on aluminum. If the machine was a more capable machine with more rigidity, better tool holding, higher horsepower, I could probably rough the profile in 1 pass. 3/8 aluminum with a roughing cutter, probably should be able to do it in 1 pass. But the tool holding is a limitation. If I push it too hard, the tool pulls out of the collet. If I push it too hard, I get shattered. And so I'm really limited by the rigidity of the machine more than the horsepower of the motor. The sanity check is looking reasonable. I don't see anything that looks insane here. So I'm roughing in 3 passes. there's a chance that I could possibly rough in 2 passes if I really wanted to minimize cycle time, but as I was learning to use the machine, I did a bunch of experiments where I was seeing how far I could push it, and yeah, I can probably push it a little bit further, but I'm not sure I really want to. Yes, the final roughing pass goes a little bit below the surface of the part and goes 15 thousandths down into the tooling plate, and this is as planned. This is completely correct. And I believe that my sanity check is fine and I'm going to be safe to run a part. I'll probably just, why not, go ahead and make sure that the finish pass is also sane before I actually put a part in place. But almost everything in NQALHA is done on tooling plates. Preliminary height looks reasonable. Pre-feed height looks reasonable. Feeding to a reasonable position. It's all looking completely correct and under control. Since I'm the machine designer, the toolpath programmer, and the machinist, I tend to think in a very connected kind of holistic way. When I'm designing a part, I'm also designing the fixturing and designing the toolpath and designing the work holding and thinking about, well, how can I make it on the machines I have? And as a result, many of my designs share a lot of commonality, and one of the common things that they all share is that they're all done on tooling plates. That is looking very reasonable. I made some off-camera, it's not a very interesting process, pretty boring process actually. I made some little spacers here over on the metal lathe. You can see them like that. And they're little shoulder spacers. And I'm going through the 7/16 bushing hole. And I chose that particular hole because it's at the extreme end of the part and I want to have the maximum rigidity at the end. The profile in the center, this part in the center, is pretty much cosmetic. It just has to look good. A tiny bit of deflection in the part in the middle, as long as the surface finish comes out nice, doesn't matter. All I care is that it looks good. This end is a fairly precise cutout because the little hinged magnet holder that it fits in is one of the few parts of the NQALHA that actually requires, you know, a little bit tighter precision than normal. So I'm going to clamp it at the end. Be very careful first time through because even though I did my sanity check, it was still the first time. cutting very nice and smooth, no chatter. The tool bit is called the aluminum shredder, and it's a kind of a serrated sleuth roughing tool, and it produces very, very fine tips. See if we can get those tips on camera here. The nice thing about these very fine tips is that, well, they don't wad up on the cutter, and they don't produce a rat nest, and also they are easier for the flood coolant to evacuate, because when doing a deep groove like this, we don't want to get the chips kind of like recutting chips over and over again if the chips get caught in the groove. So the aluminum shredder is an excellent tool. Hey, looks like I had a camera problem there. So that's looking very nice. Finishing pass is running at 30 inches per minute. The roughing pass was 3 passes at 40 inches per minute. 3 passes to get through 3/8. Like I said before, it probably, if I wanted to push it, I bet I could do it in 2. But trying to push the Tormach to its limits often results in problems. And yes, wrong tool. So that, see if you can see the surface finish is absolutely beautiful, and that is such a nice part. Everything is coming out very, very nice. So I'm going to just hit the top of the surface plate, barely run a file over it, just in case that operation left any kind of a little burr. So I am now in production on outside profile. And while the machine is working, I go over here and do a little deburring. On a lot of my parts, I have a little vibratory polisher, and the smaller parts fit nicely into the vibratory polisher. This one doesn't fit, and I kind of like the brushed look that I get with the Scotch-Brite wheel. I've got a 1-inch wide wheel on the left and a 4-inch wide wheel on the right, and I had to make a special adapter for the 4-inch wheel to go on my buffing machine. But hey, it just comes out beautifully. Unfortunately, the mill finish of my extrusion stock is not perfect, and my metal supplier doesn't treat it with the respect I think it deserves, and so I end up with a few little dings and scratches, and takes a little longer on the Scotch-Brite wheel. But yeah, in production. Profiles are beautiful. Surface finish is beautiful. Another advantage of using the roughing cutter is that it allows me to keep the finishing cutter in better condition, and the roughing cutter will take all the abuse and it'll get worn down, it'll get dull, and the finishing cutter is only barely doing a little bit of work, and it's working over the full thickness as opposed to like pecking away step after step. It's working the full thickness of the material, so it's wearing evenly over the surface of the material, over the flute of the cutter. So there's another part. I made these hold down spacers, these screw spacers. They're pretty precise and sometimes they're a little hard to get out, but hey. These are beautiful, beautiful parts and all is going well. So no reason to keep the video camera running for the rest of the production. I'll be back when it's time to drill the last operation, which is going to be a hole, a precise drilled and reamed hole that acts to hold the pin for the hinged magnet. So, see you later. So I'm moving on to the next operation, which is to drill a hole, a precision hole through this face and through this face to form an axle for the magnet ring. Now, notice that this is a magnet ring that I had in stock. It was left over from the last run. And you notice that the clearance here is very, very tight. It's probably, you can't even see a gap on video, but it's definitely within 1/1000th or 2, which is important. Keeping this hinge precisely aligned is very important because it needs to move a little bit, but not too much. So the rest of the outline is just aesthetic, and as long as the surface finish looks nice, it's fine. But the relation of the two parts and the whole really has to be precise. And so for that reason, I made a special fixture here. The reference surface that is relevant is this surface. Of course, I could reference from this surface, which was cut on the same setup on the same machine, but just to be a little bit more accurate, I'm referencing on this surface, which is this piece of aluminum, and as the part fits in this holding fixture, you can see how the reference surface references up against that little piece. So I'm going to put this in the machine. I've got the Hymer Indicator mounted in the Tormach, and I'm going to indicate on that surface. So this will, actually this, I've got a little Sharpie mark here indicating that that is the 0 reference. So I'm going to indicate to this side of the fixture, inside and out, both in X and Y. And, you know, I could probably do do just fine clamping with the soft jaws with a ledge, but it doesn't quite clamp enough of the material that I'm interested in keeping precise, so okay, so at the soft jaws in position, yeah, that's a substantially better. Let me put my little stop over here. Most of the parts that I make, I don't need to do a special setup. Most of the parts I make work just fine on my standard setups, but some of them I do require a special. So let me go over here to the network, and it's really nice having all of my parts on the network. So this is going to be work offset 4, and that's going to be G57. And see, the machine probably almost remembered. And I'm somewhat uncomfortable with that. The jaw was a little bit too close to the surface there, and I didn't think that I could get the Hymer probe. So the machine more or less remembered where 0 was, but more or less is not good enough in this shop. Okay, so probably can't see this on the video. The machine remembered its position, and then when I turned it on and caused it to go through its homing cycle with the mechanical limit switches, it homes more or less accurately, but now that I've got it zeroed with the Hymer, it tells me that it's 9 thousandths away from 0, and 9 thousandths just isn't good enough. So now I've established the 0 here, and might as well just go ahead and give it a sanity check. Just give it a manual command to go to 0 and make sure that 0 looks reasonable. And now Z0 is going to be a bit different in this case. For many of the operations, I use Z0 on the top surface of the part. Sometimes I do it on the bottom surface of the part. Sometimes I do it on the top surface of the tooling plate. In this case, Z0 is going to be on the surface of the vise. So, gotta make sure that the spindle nose is clean. And the surface of the tool setter is clean. And we have now set work offset 4. Go to the load position. And look over here that this is going to be, because this is a part that requires pretty good precision. This is one of the few parts of the NQALHA that requires higher than standard precision. And so I'm going to be reaming this hole. I'm using a 15/64 drill bit, and I always need to check the stick out here to make sure that I'm going to be okay. And yes, I am just barely okay, which I believe I've run this program before, and I believe that I'm going to be safe. So let's go ahead and put in tool number 40. Actually, I'm not right. Pay attention, dude. Tool number 51, 15/64. Plenty of stick out. Double check, triple check, then check again, then check again, then check again. Tool 51. Looks like my tool carousel is full. Might have to remove one of my tools. I'm not going to be using I'm not going to be using this one in the next part, so. And I always like to clean my tools before putting them away. So, cleaning the precision mating surface here, making sure this surface here is also a precision surface. This determines the tool length, and so I got to make sure this is clean, got to make sure this is clean, and got to make sure that inside the tool carousel that I don't get a bunch of chips that build up on this surface. Tormach actually thought about this when they were doing the design of this automatic tool changer, and they have a little air nozzle. It's what you hear going when the tool is changed, that the little air nozzle blows off the surface, the mating surface, so in case there is a chip there, there's a better chance that you're going to get a nice tight fit. Load up tool 52. And then just going to do a sanity check here. Do a dry run with no part in place. Because I've already invested quite a lot of time making these parts, and it would really suck to ruin one. So this program that I'm going to be running here is a known trusted program, completely unmodified. It worked last time it was run, but still, I treat every program as a new program the first time I run it, even old trusted ones. Okay. Position looks correct to the eyeball. Preliminary, oh, let me get the spatter shield up here. Preliminary Z height looks exactly correct. Okay, sanity check has been passed successfully. I am now confident that I'm not going to ruin my part. So, and since the fixture is loose, I need to make sure the fixture is seated against the stop and the part is seated on the ledge. Make sure the ledge is free of chips. Make sure the bottom of the part is clean. Put the part in. Align in place. While holding in place, I'm gonna clamp down the vise. Yeah, I probably don't need to worry about clamping the right side because all the action is happening on the left. So here we go. (250 RPM, 5 inches per minute on the ream operation. And it looks successful. It's a tiny bit of a challenge to deburr this inside edge, and I have to do it very carefully because this edge is one of the precision edges, and so I can't be too aggressive with the deburring. Now, I'm going to go into the other part of the shop here and get my gauge pins. So, a 250 gauge pin fits with no slop. I almost have to press it in. So there I've got my 250 gauge pin, and probably need to buy an inside micrometer someday. So let me get my gauge blocks. That measures a 1/1/8 gauge block, slides in tight but not forced. Let me go check the dimension, the design dimension, and see how close I hit it. Yes, it is within tolerance. So now, into production. So I'm not going to bore you with the last 8 parts since the program seems to be correct. The result is coming out within tolerance. All is looking good. Thank you for watching. It's been fun.